All right, continuing chapter 26 today, we're going to look at a different kind of chi-squared test. Similar but different. The story problem for today is medical researchers enlisted 90 subjects for an experiment comparing treatments for depression. The subjects were randomly divided into 3 groups and given pills to take for a period of 3 months. Unknown to them, one group received a placebo. Remember placebos? That means it's like a pill. We tell them it's medicine, but there's really nothing in there. The second group received this thing called it's a natural remedy. It's called St. John's wort, meaning it comes from nature. It's not a synthesized medication. And then the third group received this prescription drug, Posrex. After 6 months, psychologists and physicians who did not know which treatment each person received, so you might remember this is blind, and then it was unknown to the people, so that means we have a double-blind experiment. Just to remind you of some vocab. Okay, back to the story. So the physicians and the psychologists evaluated the subjects to see if their depression had returned. And we're going to decide, is there a difference between the groups, right? Because there are 3 different groups. I'm curious if their depression either came back or did not come back at the same rate. So here is a table of our data. We're going to be performing what's called a chi-square test of homogeneity. Again, like you have to know these names. You have to be able to identify which one is which. So here's our data. There were, remember, those 3 treatment groups. And then there were 2 possibilities. Either their depression came back, so you'll notice, right, like a good chunk of them, their depression came back. But in some of them, there was no sign of depression. So that tells us that it was working. So some of the placebos, it worked. Some of the St. John's wort, it worked. And then it looks like a good chunk of the Posrex, it worked. So what I'm curious is, are the percentages for depression coming back, no depression coming back, are those the same percentages for each group? Right? Like this is slightly more than half. So I'm kind of comparing, is this slightly more than half? Is this slightly more than half? Right? So we're testing to see if the percentages are the same for all the groups. That tells me if the medication worked or not. So step 1, you might imagine, is to write our hypotheses. Again, these are in English. So I might say something like null hypothesis, status quo, nothing changed. It's the same for all 3 groups. Rate of recurrence is a fancy way of saying the depression came back. So that might be the rate that depression came back. It's the same for all 3 treatments. So it didn't matter if you had a placebo or if you had an herb or if you had a prescription medication. We all got the depression coming back in the same percent or the rate. Alternatively, right, it's just say something opposite. The rate of recurrence differs for some treatments. Now, I may or may not be able to specify which one looks like it's different or standing out, but it's definitely different for some treatment. Notice again, English. No symbols, English. All right, step 2, conditions. Let's see, there were 2 conditions we had to verify. The first condition was random. Now, you may or may not remember, so I'll jump back. In our story problem, it said the subjects were randomly divided into the 3 groups. So that satisfies our random condition, and I would just note that. It says they were randomly divided into the groups. Cool. Our next condition, we need to verify that the expected counts are greater than 5. Now, last time we were able to multiply some percentages, but this time that's going to be a little more tricky. So here's my table. What I've done is I've taken out the observed values that were in these 6 boxes. And I actually added, like I wrote this, I added in this column of totals and this row of totals. So if this was your story problem and there wasn't any totals, like you'd add these up. 24 plus 6 is 30, and 22 plus 8 is 30. And 14 plus 16 is 30. And then you'd add horizontally as well. Okay, so you could fill those in if they were not provided. All right, so here's what I'm going to do. I'm going to notice that the groups are each 1/3 of the total. Right? 30 out of 90, out of my big total here. That's a third. So there were 60 people who had their depression come back. And I want to split this 60 into thirds. Let's see. Well, if I put 20 here, and 20 here, and 20 here, they're all in thirds. This row of no depression, there were 30. If I want to split that evenly into thirds, there would have to be 10 here, 10 here, 10 here. You might need to ponder that for a minute. Now, I am well aware that some of you are going to be like, whoa, Ms. Curtis, that is like way too mathy with no formulas. I don't know if I can handle that. So if you need a little trick, I'll give you a trick, but warning, it's not on your formula page. So here's another way to do this. I'm going to slide this down just a little bit so I can write at the top. Here's my little trick. If you need help calculating your expected cells, you're going to take your row total. Oh, sorry, we don't use X for times anymore. We've graduated past that. You're going to multiply it by your column total. It's supposed to say column. And you're going to divide it by the corner total. That's like the grand total. That might be a better word for you, the grand total. So I'll just illustrate that with a couple of cells. So this one right here, if I needed help figuring out that expected total, I would take my row total. That's this number right here. It's at the end of the row, 60. Times, I'm going to take my column total. That's this one if I go straight down. And I'm going to divide it by the corner total, divided by 90. And 60 times 30 divided by 90 is 20. So if you want to verify that in your calculator, like we get the same number right here. That's pretty cool. I'll erase all these lines. I'll show you that with another one. Let's see. I want to do one that's in kind of a different spot. So I'll do this cell right here in blue. So if I take my row total, let's go to the end of the row, that's this 30. Times, I want to go straight down to the end of the column, that's 30. And again, I'm going to divide by the corner, that's 90, and I get 10. So this is another way you could figure out the expected counts. Most of my students prefer this because it's a formula. How do I say it? It requires less thinking, but you would have to memorize it if you're going to use it. You would have to memorize. All right, so we'll move on. So we were checking our conditions. The condition was that the expected counts are greater than 5. So as I look through 10s and 20s, those are all definitely greater than 5. And my proof is that I've recorded all of them. So that's, again, like showing my work. So conditions are all met. That means I'm going to perform what's called a chi-square test of, oh, my brain goes faster than my hand, homogeneity. Homogeneity. Again, you have to name the test. Must, must, must. All right, so we'll go to the mechanics section. As you might imagine, the mechanics are pretty much the same that we saw in the goodness of fit. We add up our observed minus our expected. We're going to square that and divide by the expected. So I am going to show you how to do this on the calculator. However, we still have to show our work. So I'm going to go ahead and get this started. I'm going to start in the top left-hand corner. So if you're following along and you're not sure, Ms. Curtis, where you're getting these numbers from, this is my table of observed, and I'm going to start here in the top left corner. So I have an observed of 24. And if I look at my other table that is my expected numbers, okay, that's right here. Again, top left-hand corner, I'm trying to match which ones go together. So subtract 20, squared divided by 20. Now, instead of writing out what that is, I'm just going to show that I would add the next one. So I'm going to move straight across. I have a 22 minus 20 squared over 20 plus, and this is my favorite, we're just going to dot, dot, dot. Like it continues, we keep going, we follow this same pattern, and then I just show that the last one, that bottom right corner, would be 16 minus 10 squared divided by 10. So that's my chi-square, and that's how I'm going to show my work. And then I'm going to pull my answer from the calculator, including the degrees of freedom and a p-value. All right, so I'm going to have to jump around just a little bit here to show you how to get all this in the calculator. First thing we're going to start with is the table of observed values. You'll notice it's not in a list. Nor am I going to make like 3 different lists. That's too complicated. Instead, I'm going to organize it in a box. And in mathematics, we call a box a matrix. Matrix is here above the x to the minus 1 power. So second, right here is matrix. And I'm going to have to edit some of these matrices so that I can fill in the kind of format I have here. So I'm going to go ahead and push enter. And this box does not match the kind of box I have. And I'm going to tell you the truth, I can never remember which number goes first, the rows or the columns, so I'm just going to make a guess. One of these, there's 2, right, like 1, 2, 1, 2. The other one, there's 3, 1, 2, 3, 1, 2, 3. So I'm just going to make a guess which number I need to put in first. So I'll do maybe 2 and then 3. And then, oh, hey, look, that follows the same format. If I had put these numbers in backwards, as 3 and then 2, you'll notice like my box doesn't look the same. So that's what I check. I just say, you know, I don't remember which one's which, so I just try them and make sure the box has the same format. So I'm just going to put in these numbers the same way they appear in my little table there. Pretty cool. So I'm like making a table in my calculator. Don't let the name matrix freak you out. It's just a table. Okay, so that one's in. Woohoo! I might even jot down on a paper somewhere that this is matrix A, and that's my observed. Okay, so I'm going to go back to matrix, and again I'm going to edit. And this time I'm going to create a matrix for my expected. So it was 2 and 3. And if I need to, I could jump back to where we worked out all those values for the observed matrix. You'll notice the totals don't go in here anywhere. That's correct. Like we don't want any totals. 10, 10, 10. All right, now that both of my matrices are in, I can go to Stat. This is a test we're doing. And everybody should have just a plain old chi-square test. If you have a TA84 plus silver like me, don't choose the GOF test. That's only for goodness of fit. Chi-square test will take care of us today. All right, so chi-square test, it wants to know the name of the matrix. Now, my observed matrix is not in C, it was in A. So this is where it might get a little bit tricky, like a lot of steps to remember. So I have to select matrix. And here where it just says names, I'm not choosing edit. I'm just going to push enter for that matrix A. That'll make the A show up. So again, my matrix for expected is in B, so I'll push second matrix. And I just scroll down to B and push enter. That'll make B show up. All right, and then I'm ready to calculate. It's pretty cool. There's my chi-square, there's my p-value, and there's the degrees of freedom. So I'm just going to copy all of those things onto my paper, right? Because that's all I'm asked to do. All right, so if I can go back to my mechanics page, that chi-square was 8.4, so I just write that down. That was 8.4. Looks like according to the calculator, the degrees of freedom is 2. I'll show you how they got that. And the p-value is 0.149, so I might round that to 0.145. 0.015, sorry. I did not say what I was thinking, 0.015. 0.015. All right, cool. So that's our mechanics. So I've shown my work and included all relevant information there. My apologies. I said I'd show you where the degrees of freedom came from. because we have this like grid, this table, degrees of freedom is the number of rows minus 1 times the number of columns minus 1. So thinking back to like a table like this, like here's my data. Let's see, number of rows. Well, I have 1, 2 rows. So my degrees of freedom is 2 minus 1 times the number of columns. Well, there's 1, 2, 3 columns. 3 minus 1. That's 1 times 2, which gives us degrees of freedom of 2. Pretty cool. Pretty cool. All right. So our last step, now that we have a p-value, 0.015, maybe I can speak in my alpha level right here, 0.05. You might notice that I reject the null hypothesis. My reasoning, well, because my p-value is smaller than my alpha level. But I need to include a sentence. That means there is evidence that, well, evidence of what? Remember, we're always talking about the alternative hypothesis in context. So I'm really saying this. There's evidence that this thing is true. The rate of recurrence differs for some treatments. So I'm just going to write that. The rate of recurrence, that, remember, that means depression coming back, differs for some treatments. As a matter of fact, I think that prescription medication is a winner. I mean, look at this. We expected to have 10 placebos with no sign of depression, 10 St. John wort, and 10 Posterex. So Posterex was the one where the observed is actually higher for no sign of depression. So that leads me to believe that that one is the one that's creating this difference. It's working better than the rest. All right, so that is chi-square test of homogeneity.